So now today we will do a Macaulay's method related problem, right? So now in order to save the time, I have already sketched the diagram, right? So now here we have a roller support and here we have a roller support, right? Or in other words, simply supported beam, right? And here we have a uniformly distributed some loading is there, right? And now this loading has started from a point that is 2 meters from the left end, right? And this loading has continued for a distance of 3 meters, right? And the length of the beam is given as 10 meters. Modulus of elasticity is given 1 into 10 to the power 5 newtons per millimeter squared, right? And the next thing, right? So if you're going to consider the cross section of the beam, right? The second moment of area of the beam, right, is given about the center, right? So this is what I have sketched. Is the simplified beam, right? So now you know beam is something like this, right? You know that it continues, right? Okay, right? Beam is something like that. So second moment of area about the centroidal axis is given, right? That is the value we have to consider for the calculations, right? Okay. Now let's see how to solve this type of a problem by using Macaulay's method, right? Now, in order to save the time, now you know like finding reactions, right? That is a simple thing, right? So what is the number one thing? By using the equations for the static equilibrium, right? The number one thing is that we have to find the reactions, right? There is one reaction here at RA and there is another reaction here at RB, right? Okay. So in order to find that, first you can consider moments about any point, right? So if you consider moments about that point, then you don't have to worry about RA, right? So then I will directly give you the answers for the reactions, right? So now the reaction RA, right? Because you have to save time, RA is 132.6 kilonewtons. RB is 71.4 kilonewtons, right? So now we know the reactions, right? This reaction we know, this reaction we know, and this is the only uniformly distributed load that we have, right? Okay. So now let me tell you, now according to this Macaulay's method, right? I will just read that so that you can see. Now for the continuity of the beam, right? We extend the span up to the extreme end. We know what is this end? No, this end is the extreme end, right? Right, now this end is the extreme end, right? So in order for the continuation of this beam, that is what we are doing under the Macaulay's method, right? So like we are going to extend this beam with the same loading condition, right? Now what is this load? 68 kilonewtons per meter, right? So we are going to like extend this uniformly distributed load, right, up to the end of the B, right? I will read that again. For the continuity of the beam, we extend the span up to the extreme end B in order to adjust the given beam structure, right? Okay. So then now this is something that we have added, right? So in order to balance that, right, this is something that we have added from the top, right? So in order to balance that, we are again going to add the same thing from the downside also, right? Why? In order to balance, right? Because we cannot harm the original structure, right? So 68 kilonewtons per meter we have added from the top, then we have added from the bottom side also, right? Okay, now that is the way. Now, okay, so now the next thing is, now we have to write the equation, right? Now we have to write the equation. Now this is how the equation must start, right? So that is why we need the value of E and the value of I, right? Now carefully focus the beam, right? This is how we start, right? EI, right, d2y over dx2, right? So this x stands for the distance, right, along the horizontal axis, right? Then y, what is y? Y is the deflection, right? This y is the nothing but deflection, right? So now this is how you must start. EI times d2i over dx2, right, equals, so now we are going to take the moment, right, now we are going to take the moment about a certain section, right. So now we have to cut the section, right. Now the same thing that we have already done for the bending moment diagrams, right. So now we are going to select a section. So let's think that I am going to cut from here. So now this is the section that I have cut, right. So the distance x is measured from this left to here, right. So then taking bending moment, upside going will be like the left side going up will be positive, right. So you know that, right. Ra times this reaction, Ra times x. Okay. So what is the next thing, right? So then now you have this this uniformly distributed load up to here, right? So that is going down. Now consider for this part, right? Like that up to this part. So then the left side is going down. So minus. Okay. What is this length? We know this length is x, right? Then we know here to here length is 2. So it will be 68 kilonewtons per meter multiplied by x minus 2, right. So now that x minus 2 is actually this length, right. Okay, so now the next thing is that we have to consider the moment due to that, right. So if you are going to consider this uniformly distributed load, right, and you know that the resultant or the point where the entire load is acting is what we call as the center of gravity, right. So that is at the mid, right. So if you know the length, so the mid will be x minus 2 divided by 2, right. So that the center of gravity is somewhere here for this uniformly distributed load starting from here to here, right. So then we know the load that into the perpendicular distance. So what is the perpendicular distance from here to here? That is x minus 2 divided by 2. You know that, right, as same for the bending moment diagrams, right. Then consider with the other guy. Now careful. Now other guy means this part, right, the part that is added from down, right, up to here. So now we know the distance from here to here 2 and here to here is 3. Then what is this distance for the uniformly distributed load that is at down? So that will be x minus 5. Okay, see. So what is this distance up to the section A, section S, right, up to the section X, right. So that is x minus 5. But because of this loading, the left side will go up, right. So then that will be positive, right. So that will be positive, right. 68. The length it has continued is x minus 5, right. X minus 5. And then what is the point where the entire what is the center of gravity for that load? That is somewhere here. So then the perpendicular distance will be from here to here. So x minus 5 divided by 2. Alright, so now let's simplify this, right. So now E I d2I over dx2 equals, what is Ra? Ra we have calculated, that is 132.6, right. 132.6 x minus 62 divided by 2 is 34, right, minus 34, right, minus 34 x minus 2 whole thing square, right. Then positive 68 divided by 2 is 34 x minus 5 whole thing square. Is it correct? Yeah. So now you must know how to obtain up to this point, right. Okay, so then now actually our target is to find this y. So what is the thing that you should do? Just integrate both the sides. Integrate both the sides with respect to x, right. Integrate with respect to x, right. Integrate this side, integrate this side, integrate this side with respect to x. That means put the derivative dx. Now you know about integration, right. So this is not about teaching integration. Integrate with respect to x, dx, integrate with respect to dx. So if you integrate this side, right, if you integrate this side, you will be having what? E I dy by dx, right? So if you integrate d2y over dx2, right? So what is the answer that you will be getting? Huh? So then you will be getting dy by dx, right? So that equals 1, if you integrate this one, 132.6 times x, 132.6 x squared divided by 2, right? The minus 34 times x minus 2, 2 plus 1 is 3 divided by 3, right? 2 plus 1, 3, right? Then next one, if you integrate this z, you will be having 34 divided by 3 times x minus 5 to the power 3. And one more thing you have to add, that is the arbitrary constant, right? Constant C1. Arbitrary constant. You know about that, right? That constant C1, right? Now, okay then. Now, so then, what is the next thing? Again, integrate this. Now, this guy that you obtain up here, again integrate this guy with respect to x, right? Again integrate that. So now integrate this guy, right, with respect to x, right? So then you will be getting ei dy by dx if you integrate. If you integrate dy by dx, right, what is the answer you are getting? If you integrate dy by dx, you are getting eiy, right? Then 132.6 divided by 2 times integration of this one. What is the integration of this one? X cube divided by 3. Integration of this one, minus 34 divided by 3. Then x minus 2 to the power 4 divided by 4. Integration of this guy, plus 34 divided by 3, x minus 5 to the power 4 divided by 4, right? Okay. So then if you integrate this c1, right, you are getting c1x. If you integrate c1, you will get c1x. Then the next integrating constant, c2, right? c1x plus c2. So this is the equation. And if you further simplify this, you are getting eiy equals, if you simplify this one, 132.6 divided by 2 into 36, then you are getting 22.1 x cube. 22.1 x cube. Then minus, if you simplify this one, you are getting, here we have 34, here you have 12. So if you simplify that, you are getting 2.83, right? Okay, so you are getting 2.83 x minus 2 to the power 4. Then for other guy also 34 divided by this one, yeah. So other guy also you are getting 2.83 x minus 5 to the power 4 divided by 4, right? Not divided by 4, x minus 5 to the power 4, right? You are not getting 4, right? X minus 5 to the power 4. Then c1x plus c2, that's it. So now check whether you have obtained this answer, right? eiy equals 22.1 x cube minus 2.83 x minus 2 to the power 4. There are lots of simplifications, right? Then 2.83 x minus 5 to the power 4, c1x plus c2, right? So that's the target, right? Right. So that's it. Now we have to find the constant c1 and c2, right? Now the first boundary condition, right? Now carefully focus, right? Let me tell you. Now please arrange this equation according to this eiy. Now there is a story, right? Let me tell you what. Arrange this equation such that you are getting only x powers, right? Like x powers means not like x minus 2 to the power 4, x minus 3 to the power 5, without considering this type of terms, right? Just consider only the terms with the powers of x. See, something like this, 22.1 x cube, then plus c1x plus c2. These guys are also there, okay, but doesn't matter. So let's write minus 2.83 x minus 2 to the power 4 plus 2.83 x minus 5 to the power 4. Just write that, right? But when considering the application of limits, just consider only terms with that a whole number powers of x, right? Or not whole number powers, no, here also we have a whole number, no. It's not like that. Just don't consider this type of sets, right? Just consider sets like this. Then applying for the first boundary condition, right? So we can apply these boundary conditions, right? So now see, at x equals 0, when x equals 0, y equals 0, right? So if you use this boundary condition, this side will be 0, this is 0, plus this is 0, then this side will be C2, then C2 equals 0. Now this is how you should solve, right? So other than that, if you consider these two guys also, then for C2 also you will be getting a value, right? So now you know that C2 equals 0. Actually this is the way to solve, right? And the next thing, now let's use another boundary condition, right? Now let's use the other boundary condition, right? Now that is, now we know that when x equals 0, y equals 0, then the other one is that right, when x equals 10, right, I will erase that, right? So now we know that now we know that C2 equals 0, right? The next condition is that when x equals 10 meters, then y equals 0, right? So now put x equals 10, right? So now if you put x equals 10, right? EI, when x equals 10, y is 0, right? So put 0 here. So here now I am not going to do simplifications, right? It will take time. Just put x equals 10 here and put x equals right, and put x now the next most important thing. Now this is our standard equation, right? Consider this equation, right? So now to this equation, this side is coming as 0, right? Because y is 0. Here put x equals 10. Here also put x equals 10. You have to put, right? Here also you have to put x equals 10, and here also you have to put x equals 10, right? Okay. So here also you have to put x equals 10. Now C2, we know that C2 is 0, right? So now you can find a value for C1. Now check your calculations. So if you do that, you are getting value for C1 as C1 equals minus 1226 minus 1226.55. Okay. So now let's write the final equation, right? Now equation for the deflection, right? So that is what we are going to do. Equation for the deflection is EIY equals right. Check your answer, okay? 132.6 divided by 6x cube, right? But I think 132.6 divided by 6 will give you 132.6 divided by 6 will give you 22.1, right? Okay, then we'll write according to that format, right? Then it is much more simplified, right? So 22.1 x cube, right? So then minus 34, yeah, minus 2.83 x minus 2 to the power 4. Then positive 2.83 x minus 5 to the power 4. Then minus 1226.55 times x, right? So this is the equation for the deflection, right? Okay. So now we have solved that also, right? Now, what do they ask? They ask us to find maximum deflection and position of the maximum deflection. So how to find that? So, okay, now focus, now calculations you can do, right? I'm only giving you the steps, right? So now you know that at maximum deflection, Now you know that at maximum deflection, right, when the deflection is maximum, you know that dy by dx equals 0, right? At the maximum deflection, dy by dx equals 0. So now consider the equation that we have previously obtained with the first derivative, right? Because previously we have obtained an equation with the first derivative, that is, I will write it, ei dy by dx. Can you remember the one before the last integration, right? dei dy by dx equals you know that, right? Okay, 132.6 divided by 6, no, 132.6 divided by 2, 132.6 divided by 2 x squared, right? Right, but the one before the last integration, right? Minus 34 divided by 3 x minus 2 cube plus 34 divided by 3 x minus 5 cube, x minus 5 cube, minus the constant c1 only, you remember that, right? 1226.55, right? Okay, so now we know that at maximum deflection, definitely dy by dx equals 0, so this side will become 0, right? Okay, that side will be 0, right? So then you have to solve this, you have to solve this guy, right? It's mathematics, right? So then you can obtain the answer for x, right? So carefully check your simplifications. Now at last you will be getting a quadratic equation. If you simplify that, you will be getting a quadratic equation like 35.7 x squared minus 714x minus 2552.55 equals 0. So you will be getting a quadratic equation. So if you solve that, you will be getting two answers, because you know that if you solve a quadratic, you are getting two answers. So first answer x1 equals 15.34. Second answer x equals 4.66. Now you know the length of our beam is 10 meters, so definitely this cannot be the answer. So the possible answer where the maximum deflection occurs is x equals 4.66, right? So the maximum deflection occurs over there, right? What is the next thing? Now you know the point where the maximum deflection occurs. And right, so here is okay. So what is the next thing? Next thing is find the maximum deflection. You know where the maximum deflection occurs. Then find the maximum deflection. Then use this equation. EIy equals that. Put x equals 4.66, right? The value for E you know, value for I you know, right? If you put that, you will be getting a value for y as, I am only giving the answers, you go and check. You are getting an answer for y as y equals minus 0.1034. Minus 0.1034, that means 103.4 millimeters of deflection, right? Along the, and you have to specify that, as it is negative, you have to specify it. Along the opposite direction of the, support reactions, right? Along the opposite direction of the support reactions, right? The next one again, it has deflection at the mid of the beam. Okay, so the length of the beam is 10, the mid is 5, right? So then again use this equation, right? Put x equals 5, right? So then I will give the answer for that. So that also you will be getting a negative answer, again along the opposite direction of the support reaction. So that answer, when considering the deflection at the mid of the span, that is 102.8 millimeters, right? 102.8 millimeters. So please check your answers, right?